We'll talk today about Chapter 4, Applications of Derivatives, Section 4.1, which is about extreme values of functions on closed intervals. We want to first give a definition of about absolute maximum, absolute minimum. What's an absolute minimum? Extreme values, actually, by extreme values we tell that we mean that by extreme values, as I said, we mean absolute maximum value and absolute minimum value. So let's give a definition. If you consider a function and if you consider a graph of a function, you will see that if you look at the whole domain of the function, at some points the function takes the biggest value. It's the biggest of all the values it can take, and we are going to call it absolute maximum value on the domain D at a point C. And when you look at the graph of an f, you're going to be able to plot a point C where the function takes the smallest value of all the values it takes, and we call it absolute minimum value on the domain D at the point C. Okay, mathematically, actually, we let me explain it here a little bit better, maybe. Let's see. Okay, so here we mean, so this is going to tell us that for all x in the domain, f of x is going to be f of x is going to be less or equal to f of c. That's how f of c becomes the absolute maximum. But on the other hand, here, if you look at the other one, which is this, so it says f of x f of c is going to be the smallest of all the values it can take. Okay, that's mathematically how we explain it. Let's continue. So here's an example you can see. In this example, we have cosine x and sine x. And what's the domain? The domain is, let me use this color. The domain is between negative pi over 2 to pi over 2 for both functions. And let's show, I'm going to use red color for the absolute maximum. Let's concentrate on the cosine x. See, this is the biggest value for cosine x in here, and that's why we call it the absolute maximum value. Absolute maximum value is what? It is 1, and attained at x is equal to 0. This is for y is equal to cosine x, yeah? And now what is the absolute minimum for that function? So I'm going to use blue color for that. Okay, for absolute minimum values for cosine x. Okay, so there are actually the absolute minimum value, its smallest value it can take in this interval. Absolute minimum value is 0, and attained at x is equal to minus plus pi over 2. So there are two x values where it takes this minimum value. That's okay. Okay, and let's get the sine x. For sine x, I should use another red color. So the blue graph is the sine x, and where is the biggest value for sine x? It is attained. Okay, this is the biggest value, so I'm going to here. So absolute maximum value for sine value is what? Let's get, this is 1, but it is obtained at x is equal to pi over 2. On the other hand, it has a minimum value right here, so I'm going to use a green color maybe to differentiate things here. Okay, for the absolute minimum, absolute minimum of sine x is this, absolute minimum value is what? -1, and at which x it is attained at x is equal to -π/2. Okay, all right, so that's how you would but this is as you see, the domain is between -π/2 to π/2. Okay, so let's move down. Okay, that's it we have here. Let's move to the next page. Let's look at this example in our book. Okay, so again, so what's the domain here? Look, the domain is important here. The domain is everything here. Okay, all real x's, all reals. Yeah, this is the domain here. The domain is different. So 0 to 2, the domain is just 0 to 2 here. Yeah, so that makes the difference between these two functions. 0 to 2 again, but be careful, 0 is not included here. Okay, here both 0 and 2 included. Here 0, 2, but none of the endpoints are included. Okay, so I'm going to kind of do it like this. This makes a big difference here. It is going to tell us that, for example, in this case, we are going to have only absolute minimum but no absolute max. Okay, so I'm going to write absolute minimum value is 0. Okay, at 0, but absolute maximum doesn't exist, does not exist, because the domain is all real. So the function takes infinitely many values here, positive values here, right? So here, that's why it says absolute minimum only, so we don't have absolute max. And here in the second picture, we are going to just look at here. So we have the absolute maximum value and we have the absolute minimum value, right? So so I'm going to write absolute maximum value is what? At 2 it is 4, attained at x is equal to 2, and absolute minimum value is what? 0, attained at 0. So we have both of them. Okay, but here let's get the third one down here. See, here we have an absolute max. This is absolute max, but no absolute min. Okay, only absolute max, because this is not included. Okay, no absolute min. No absolute minimum value here. Let's get here. Both of them are not included. Look at that. So no max, no min. Okay, none of them. This is a good example to show that when we should make a decision about the absolute min, absolute max. Okay, I think this is it. Thank God we have a theorem that's gonna help us this is called the extreme value theorem. This extreme value theorem says if you have some certain conditions, then it is guaranteed that you're going to have both absolute max and absolute min. So what are those conditions? First of all, f is going to be a continuous function, and it's going to be continuous on a closed interval like this. Okay, it has to be the domain, it has to be closed and bounded like this, a to b. Yeah, this is like that. This is important that we have this. And then if we have just this, yeah, continuity, this is number 1, and closed interval like this, number 2 conditions. If you have these two conditions satisfied, then f is going to have both absolute max and absolute minimum value, both of them guaranteed. Okay, on this in this interval. Okay, so that's very good. Okay, we have that. Let's see it. Okay, let me show you. Okay, I'm going to show you the domain here. Look, the domain is closed and bounded. Look, this is our domain here, and the domain A to B included, both of them. And here is the pardon. Okay, look at this. This A is included as well. Okay, A to B. Domain is bounded, closed and bounded like this. Okay, when you have that, extreme value theorem says you're going to definitely have maximum and minimum, and I'm going to show you that we have the maximum here. It's the biggest value. Okay, this is it. And we have the minimum value. It's here. Okay, here's another example. Here's the absolute max. Here's an absolute min. So we definitely have it. Here's a closed and bounded interval. Here's maximum, absolute max, and here's absolute min. Okay, here closed and bounded interval, and function is continuous. You see that, right? So here's absolute min, here's absolute max. Okay, we have that. So in other words, be careful here. Let me see. Where's my cursor? Okay. So here we have the absolute min and max inside the interval. Here absolute max and min at the endpoints. Here we have absolute max in the interior point and absolute min in the at an end point. And here we have absolute min in an interior point, and interior point, I should say. Interior point means inside the interval. Interior point. Okay, this is one, and end point means it's the end of the interval, right? End points. Okay, so here you have the minimum at an interior point. Here's you have the maximum at an end point. Okay, all right. So let me see whether I have any other things here. No. All right. So let's look at this function. Okay, so the question here is, can we apply extreme value theorem to this function? Okay, question, let me write this in red. Okay, question, is extreme value theorem applicable here? Okay, that's the question. And what are the conditions for extreme value theorem? We have just continuity, and the continuity has to be on a closed and bounded. Okay, is extreme value theorem applicable here? So first thing we see that okay, you can see the domain here. Actually, you can see the domain 0 to 1. So the domain is important for us. So let's draw this, and you see on the domain, do you see that the function is not continuous at 1? At 1 just jumps down to this value. So we have that here there's a jump, as you would see. Okay, and here from here to here there's a jump. There's a jump. So f is not continuous. F is not continuous. Not continuous. So it doesn't satisfy the very first condition of extreme value theorem. The domain is 0 to 1, no problem. So it's a bounded closed domain. It's okay, but this is not okay. Okay, this part is failing, so you won't be able to find extreme value theorem. I mean, if it was applicable, you would be able to find the largest value. But here, as you will see, we don't have the largest value. Do you see that? No largest value. No largest value here. There's a smallest value. This is smallest value. This is smallest value, but no largest value. We don't have them both. Okay. So let's continue. Let me see whether I have here anything else down here. No. Okay. Let's continue here. Next, we are going to talk about local max, local minimum value. These are just a little bit different than absolute max, absolute minimum, because we just look at the graph locally. Okay, locally you may have, if you consider locally, you may have more than one local maximum value. Okay, so or local minimum value. But in the absolute maximum and absolute minimum value case, you have a unique absolute max, unique absolute min, if there exists, of course. Okay, so what is a local maximum is locally we look at it, and locally this at c, f of c is going to be bigger than all the points all the values f of x nearby, okay, lying in some open interval containing c. It's nearby if it is the case. So let me get that highlights here. Here local max means we are looking for this relation, just a sec, we are looking at this relationship but in some open interval containing c, not globally. We are not looking all domain, okay, we are looking at just single on an open interval around c. And similarly local minimum if we highlight, local minimum value is going to be attained at c if f of c is going to be smallest of all the values in some open neighborhood of c, okay, like if you see it in the picture here, let's see it in the example, right? So let's look at the c point. If you consider neighborhood of it, not everywhere, you're not going to look at everywhere, so neighborhood of e, neighborhood of a here, just a close by interval around it, okay. Maybe this is not right, we have to erase because it's not going to go to the right of b because the domain is from a to b, yeah. So we are going to go until b, just nearby, okay, we are not going to pass. Okay, so if you look at these locally, see here, this is the biggest value in here, so therefore it's the local maximum. Sorry. Here, okay. All right. So here we have the local maximum because no greater value of f nearby. Okay, let's get around e. Around e, let's get the graph around e. Like we can only look at these values. This is the smallest of all such values, right? No smaller value than this, so it is going to be a local minimum value. Okay, let's look at the d. Okay, so at d, let's just look at this highlighted area. This is the biggest of all these, so therefore it is both absolute maximum and local minimum, local maximum, because look, it is the biggest of all these values you can consider. You're going to look at the whole interval, and this is the biggest of them all, right? The whole interval is this actually. Okay, the whole interval is a to b here, a to b. Okay, so you're looking at a to b. Maybe I should draw it a little bit close by because you can consider I'm drawing the sentence here. Okay, so here I'm talking about a to b here. Look, a to b. So this is the domain. So I'm going, if you look at it, so this is the biggest of all these big values here. Okay, so therefore it's absolute maximum, but at the same time you can consider it as a local maximum as well, because if you look at it locally, it's the biggest value of them all. Let's look at this d. Let's draw it locally. We are going to just look at these values. This is the smallest of all such values, so it's the local minimum value. Okay, no smaller value nearby. And let's look at this a. Okay, graph. So this is the smallest of all such values, so it is the local minimum. It's local minimum, but at the same time it's an absolute minimum because you consider all such values. This is the smallest of all such. This is the local min. This is the local min, but this is the smallest of all such local mins. Okay. So how many local minimum values do we have? 1, 2, okay, and 3. We have three local minimums, and this is the smallest of them all. So therefore, it deserves to be called absolute minimum. Let's look at the maximums, local maximums. This is a local max. This is a local max, and we don't have any other. And which one is the biggest? This is bigger than this one, so this point deserves to be the absolute maximum value at d. Okay, all right, so let me erase this. Okay, let's go down if we have any other here for you. I think that's it. Alright, so let's see what we have next. Okay, so let's get this one now.